Something we encounter very often in working with vectors is the need to decompose a vector as a sum of other vectors going in a particular direction. A standard example is, suppose we have an object rolling down an incline. So this object is being accelerated at 9.81 meters per second squared straight downward by gravity. But what we really want to know is how much of that is going into the motion of the ball down the slope. So we want to write the acceleration vector as the sum of a vector parallel to the incline and one perpendicular to it, and then throw away the perpendicular part. So let me call the acceleration vector u, and let v be any vector pointing in the direction of the incline. So we don't know, we're not given the solid blue vector, that's what we're trying to figure out, but we could at least know some vector pointing in the direction of the incline. Now, if we call the angle between these theta, then the vector we're after is a vector going in the same direction as v, and then where the length is length of u times cosine of the angle theta between them. So another way of saying what we're after is we need a way to calculate the angle between two vectors in terms of their components. So let me just give you the formula first and then explain it. If u and v are vectors, we define their dot product to be where we multiply their corresponding entries together and then add those up. So for example, 1, -1, 3, dot 2, 0, 1. This will be 2 plus 0 plus 3 is equal to 5. And the dot product of two-dimensional vectors works the same way. So for instance, 2, comma, -1, dot, -1, comma, -2. This is -2 plus -1 times -2 is +2 is equal to 0. The dot product is sometimes called the scalar product, since it's a way of multiplying vectors that gives you back a scalar rather than another vector. Also be careful, sometimes the dot product is written as u and v in angle brackets. So this looks like a vector whose entries are u and v. It's not, it's just a different notation people sometimes use for this. Again, we won't use that in this course, but you might encounter it elsewhere. And if they're doing this, they'll probably call it the inner product. As a key example, if we dot a vector with one of the standard unit vectors, I, j, and k, we can see that that will extract the x, y, or z components of the vector. So in general, you can think of the dot product as measuring the u-ness of v or the v-ness of u. That's kind of vague, but more precisely, it turns out that the dot product of u and v is equal to the length of u times the length of v times the cosine of the angle theta between them. So we saw before, if we just took length of v cosine theta, that would be the length of the projection of v onto u, or vice versa, if we threw away the other term. So including both lengths in the product is sort of a way of making this balance so that it's the u-ness of v is the same as the v-ness of u. Anyway, so this is the more precise formulation of that. Okay, so how do we see this? I'm going to give a slightly different proof than the book does, and I'm just going to do this in 2 dimensions for simplicity, although it is also true in 3 dimensions. So let's say our vectors are u is u1 and u2 in component form, and then v is v1, v2 in component form. And what we're going to do is, so imagine we have a 2D coordinate system here, is we're going to instead write these in polar coordinates. So let's say u makes an alpha, or an angle of alpha with the x-axis. Then u1 will be length of u times cosine of alpha, and u2 be length of u sine of alpha. And then if beta, similarly, if beta is the angle that v makes with the x-axis, then v1 will be length of v cosine alpha, or cosine beta rather, and v2 will be length of v sine beta. But now this angle theta between them, So that's going to mean that beta is alpha plus theta. And so now we'll use the angle sum identities, which tell us that cosine alpha plus theta will be cosine alpha cosine theta minus sine alpha sine theta. And sine alpha plus theta will be cosine alpha sine theta plus sine alpha cosine theta. So now we can go and we rewrite u1, so u dot v, this is going to be u1 v1 plus u2 v2. Now we expand, so u1 is u, length of u, cosine alpha, now plus, so cosine of alpha plus beta, this is going to be length of v times cosine alpha cosine theta minus length of v sine alpha sine theta, and then plus length of u sine alpha, and now length of v cos alpha sine alpha plus length v sine alpha cos theta. Okay, so this looks really big, but now we get some cancellation. So if we distribute this over to here, then that's going to be u, length of v, cosine alpha sine theta, and we're going to also get that here. So we have both cosine and sine of alpha and sine theta. So these terms cancel each other out. And now we can simplify the remaining terms. So let me erase a little bit here to bring this up. So now we've got u, length v, cos squared alpha cos theta plus length u, length v, sine squared alpha cos theta. But since cos squared alpha plus sine squared alpha is 1, this becomes length of u times length of v times cosine theta, which is what we were after. Finally, the dot product obeys several algebraic rules. We can take the dot product in either order and get the same thing. Or in other words, the dot product is commutative. Next, if we scale one of the vectors before dotting, we can do it to either of them and get the same thing. Or we can dot them together and then multiply by the scalar at the end, and we'll still get the same thing. Then, if we sum two vectors, v and w, and then dot those with a third vector, u, that'll be the same as dotting each of them with u and then adding those numbers together. So we say the dot product distributes over addition. And this is the main reason we call the dot product a product. There's many different kinds of multiplication you can do with vectors, but for something to deserve to be called a multiplication, distributing over addition is the most important property of multiplication. Then if we dot a vector with itself, we get back its length squared, and any vector dotted with the 0 vector gives 0. So let me show you how to prove the second of these, for instance. So let's say u is u1, u2, u3, and v is v1, v2, v3. So cu.v will be cu1, cu2, cu3, so this is cu dot v dot v1, v2, v3, and so that's c1 or cu1 v1 plus c u2 times v2 plus c u3 times v3. And of course, since addition of, or multiplication rather, of ordinary numbers is associative, we can, so if we bracketed it instead like this, then that would be giving us u dot v and that times c. So that's what that would correspond to. And then if we moved the c past the u, we could also write u1 cv1 plus u2 cv2 plus u3 cv3, and parenthesizing like this, that is the definition of what u dot cv parenthesized like this would be. But of course, all of these three expressions are equal. So the three vector expressions are equal. Now, as a kind of converse to the last property, we also have u dot v is equal to 0 if and only if one of u and v is the 0 vector, or the angle between them is 90 degrees, so a right angle. And this follows pretty quickly from the equation that it's the product of the lengths times the cosine of the angle between them. So if we just have three numbers, then the product of these numbers is 0 if and only if at least one of them is 0. So you can't multiply non-zero numbers together and get 0. Okay, so one of, if this is equal to 0, then either u or v has length 0, or cosine theta is 0. So cosine theta is 0 if and only if theta is 90 degrees, or pi over 2 radians, and the length of a vector is 0 if and only if that is the 0 vector. So the 0 vector is the only vector with length 0. So we make the following definition. We say that u and v are orthogonal if their dot product is 0. So this is just another word for perpendicular, as long as you make the understanding that the 0 vector is perpendicular or orthogonal to everything.